Welcome to Homework Lib.
Hi, so for this question, the first thing that we are going to do is write down our reaction that we have in place, right? So we know that this is going to generate H plus the associated anion over here, okay? And what we're going to do is doing our ice table, initial, change, and at equilibrium. So we know that all of this is in a 1 liter solution. So the amount of mole that we're going to end up with, it's going to be equal to the concentration in molar, right? Because the molar concentration is amount of mole divided by the volume in liters. Since the volume is always going to be 1 liter, it doesn't matter the amount of mole that I put. In this case, it's going to be the same as the concentration. So we can place in here molar, molar, and molar. So what we're starting with is a 0.43, 430 molar concentration of the acid, and then we have 0.190 molar concentration of the salt associated to this ion. Remember that when we have the salt and we put it in water, we're going to have sodium plus the associated anion. So that is why I can put directly the amount of substance generated over here, since we have a 1-to-1 relationship in between the full salt and the associated anion. So now the next step is use the Ka for this acid in order to know what is going to be our final pH, because we can assume that at the beginning we're going to have a zero amount of H+. Now the amount of change, let's call it X, that is the portion of the acid that is going to dissociate. We are going to add X on both sides of this equation. And at the equilibrium, we're going to have 0.430 minus X, X, and 0.190 plus X. Now, let's write down our acidity constant for this reaction, which tells us that this is equal to the concentration of H plus times the concentration of the salt anion that we have, divided by the concentration of the acid that we began with. Replacing these concentrations with the values at equilibrium, we end up with X 0.19 plus X divided by 0.430 minus X. And this is going to be equal to the given Ka, that is 1.8 times 10 to the minus 5. Now, since the Ka is 1.8 times 10 to the minus 5, we know that we are going to have a small amount of dissociation, so we are expecting that X is small. How small? Well, let's first assume that the result is going to be that the concentration of the lower of these numbers is going to be much larger than the value of X. In order for that to be true, when we solve for X needs to be lower or equal than 5% of the concentration that I'm comparing. So in this case, 5% of 0.190. So we have two options. The first one would be to solve the full quadratic expression that comes from doing this, which we could do it. It is quite easy to do in a calculator, but it's often not necessary, as you will see in this case. And the other one is to make this approximation. With this approximation, the value of 0.19 plus X, it's going to be approximately 0.19. And the value of 0.1443 minus X is going to be approximately 0.43. So we can replace those directly in our expression for Ka. So we have 1.8 times 10 to the minus 5. On the upper side, we're going to have 0.19 times x divided by 0.43. Solving for x, it's 0.43 times 1.8 times 10 to the minus 5 divided by 0.19, and the value for x turns out to be 4.07 times 10 to the minus 5 molar. Remember that this x was the amount of H plus at equilibrium in concentration directly. So, since this is the concentration of H plus, we can calculate the pH as minus the logarithm of that concentration, which is minus logarithm of x, which is 4.39. And that would be our final pH. Okay, so we did all of this. Now let's verify just that our approximation is correct. 4.07 times 10 to the minus 5 indeed is much smaller than 5% of 0.19. So we can use that approximation. It is going to give us exactly the same, well, not exactly, but quite super close to the result of doing the quadratic expression that I was mentioning. And that would be all for this problem. That is the final pH.